Welcome everybody. In this video we're going to use the SIR model that we've developed to investigate how many lives were lost because people didn't wear masks in the period up to Memorial Day 2020. Let's start by quickly reminding you about where you can find these materials. They're at circle4.com/biophysics, and if you click on the free sample chapters link, it'll take you to the chapters page, which are for a book that I'm working on with Cambridge University Press. Now, as we've talked about before, chapters 1, 2 and 3 are an introduction to this approach, and we're now up to chapter 12 and section 12.6, which is on page 67 of chapter 12. So before we can get started with investigating how many lives were lost because people didn't wear masks and follow social distancing, before we do that, we'll need to investigate how to model the transition from the initial exponential growth period that we've already talked about and the period of social distancing. So let's remind you about what we've done before. We've developed an exponential growth model which models the initial growth of the number of infections per day, right? Remember, this graph has the infection rate per day, and on the x-axis we have time in days. And we also developed a model of social distancing, which is this part of the curve. The one thing we didn't do was model the transition period between exponential growth and the period of social distancing. So that's what we'll talk about now. So the idea is that we'll make the infection rate constant be a function of time, so that during the initial exponential growth, Ki will be given by K1, and during the period of social distancing, Ki will be given by K2. T12 indicates the transition time between period 1, which goes with K1, and period 2 that goes with K2. So question 1275 is about investigating that idea. And here's my spreadsheet answer that I developed. The chapter will guide you through how to get to here. So it has a parameters column with things that hopefully are familiar by now. Capital N is the model population size, delta T is the time step, tau I is the mean infectious time, Kr is the recovery rate constant, K1 is the new thing. It's the value of the infection rate constant during period 1. N0 is the number infectious at the beginning of the model. R0 is the basic reproduction number. And K2 is the infection rate constant in period 2, the period of social distancing. T12, as we just talked about, is the transition time, which is set at a value of 30 days to start out with. And Q is the thing that we're going to use to find the quality of fit. But we're not going to use that just now. Alright, so in the spreadsheet there's a column here, Ki, which is now the value of the infection rate constant. Okay, so what happens when you change T12 is, well, actually, before I do that, let's talk about what the model is doing. So it's on the exponential growth, and then it jumps down and goes on to the period of social distancing. Now, if you have a look over here on the semi-log graph, right, the infection rate constant, the way it changes, the infection rate, how it changes with time, you'll notice that the period of social distancing in the model have the same slope, and that's because we're using the value of the infection rate constant that we actually fitted to the grey dots. So as we change the time from 31, make it a little longer, 32, 31, enter, right, you'll notice that the curve went up, and if I hit 32, it goes up again, and if I hit 33, it goes up again, 34, goes up again, 35, and then if I do 36, you'll see that I've gone too far. So let's go back to 35 because it looks about right. So the idea is that you have to go up to this very high value before it jumps back down to get a value that's approximately correct for the period of social distancing. And there's a big problem with that, right? That's not what actually happened. What actually happened was the data just kind of smoothly went up to the period of social distancing and then leveled off. So there's a problem with this approach of just making a switch between not social distancing and social distancing. So how can we fix it? Well, the idea that we had in for changing the infection rate constant is that it all happened at one time, which would mean that everybody in the whole model population went from not social distancing, right, at K1 to social distancing all at the same time. And that seems unlikely, and in fact, if you recall what happened in America at the time, was that some states started doing it and some other states didn't. And of course, there's also the variation between individuals in the states as well. So the idea is that we can spread out the time that people adopt social distancing. And what we can do is we can use this bell-shaped curve that should be familiar to you from high school and maybe chapter 8. And it's the Bell normal curve, right? Or a Gaussian distribution, as physicists would like to say. It could have T12 would still appear. It would now be the mean of the distribution. It would be the average time that people adopted social distancing. So the time here, the way this, let's talk about this function. So P of T is the expression that I use for the thing on the vertical axis, which is technically a probability density, and I actually have a video talking about probability densities. But anyway, you can just think of it as being the normal distribution if you like. And Excel produces a function that's called norm.dist, and T is the thing that tells you where you are on the time axis. T12 is the mean of the distribution, so it tells you where the peak is in the normal distribution. And sigma 12, remember this thing, Greek letter S. If you've forgotten, go to the video about the Greek letters go green. Anyway, sigma 12 is the standard deviation of the normal distribution. So that would be one standard deviation on either side, and this would be two standard deviations on either side, and then 3 would be, about where the transition has been completed by pretty much everybody. And 3 on this side would be when basically nobody was doing social distancing. So the idea is that the normal distribution can give us a spread in the time of adoption of social distancing. The problem is that isn't what we actually want. What we actually want, oh, and I forgot to explain, false means that we want the bell curve, right? The thing that we actually want to use is the one that has exactly the same norm.dist. Here it is, norm.dist. Same T on time, same T12, which is the mean, same standard deviation, which is here, right? That's one standard deviation on either side. What true does is it makes it the cumulative probability of the normal distribution. So the mean is the place where half of the people have done it, right? Have done the transition. So that's 0.5. And so this function, what it does, and it's in Excel, and I'm going to call it capital F of T. What it does is it goes from 0 when nobody's done transition to social distancing, up to 1 when all the people who are going to do social distancing have started doing it. The idea is that you can then calculate Ki of T using this formula, which says that it's K1 at the beginning when F of T is 0, and that as F of T approaches 1, this expression is multiplied by K2 minus K1, so eventually when F of T is 1, it's K1 minus K1 plus K2, which is just K2. So that's how you get the smooth transition, which has a mean transition time of T12, and it has a standard deviation of sigma 12, and here's 2 standard deviations, and then at 3, that's when the transition is pretty much complete. Okay, so let's see how that works. Okay, so in the chapter, we actually go over a couple of ways of doing this before we get to the question we're going to do. And that kind of leads us to the 2 equations that are here, which I'm not going to go into the details of, but just suffice it to say that they look a little weird, but part of the reason is they actually correct for a problem with using a time step of 1 whole day for the initial growth period. Okay, so if we click on this link to the Gaussian spreadsheet and then open Excel, you'll see this spreadsheet, and if you click Enable Editing, then you can edit the spreadsheet. And before we get into the details, let's go through some of the things that we need to talk about. So once again, we've got a parameters column which has the same parameters that we were talking about before. N, delta t, tau I, kr, n naught, k1. Now there's an additional thing, td, which is the doubling time that's calculated from k1. The basic reproduction number, r0, k2, the infection rate constant for the period of social distancing, t12, which is the transition time, and sigma 12, which is the standard deviation of the transition. All right. And then in the SIR model table, which is now pretty big, there are a bunch of things in it that we need to talk about. One is F, which we just talked about, and here's KI that's calculated using that formula. So let's just click in there and see how it does. So you can see that it's equal to K1, right? A13 is K1 because it's blue, plus F, which is calculated here, and then it's in parentheses K2, the purple, minus K1, which is the blue. So that's how the formula for K1 is implemented. And then R1 is calculated with the same formula, but now instead of using a parameter for Ki, we're going to use the variable Ki. And then the rest of the spreadsheet's kind of things that we've talked about. Here's the USA data reported by the European CDC. And then we have the residuals, the square of the residuals, and then the P is here because we're actually going to plot that. So these graphs are actually from an earlier question, and one of the things that I just wanted to explain with this spreadsheet is that we're making a table over here where this column R has N naught values for various questions, right? So this column is questions. N naught are the values, and you'll see this value is actually copied down here. And this formula is calculated using the value of N naught way over here in the left-hand column. So these are just links to the values that are in the headings for this column. So R naught is a link back over here to that cell. And let's just pick another one, sigma 12. So click here, that should be a link to the cell that contains sigma 12, there it goes. And why are we doing that such a weird way? Well, it means that when we change something, like I can enter this row here by just highlighting that row, then hit Control C or Control C or Command C on a Mac, and then click down here and do Control V or Command V. And you'll see it's weird, but you have to click on this thing here, Paste Options, and select Paste Values. And then it copies them as numbers, right? Because these were actually formulas to other cells. And what this does is it allows you to copy all those, how many are there? 7 things all at once, which is kind of convenient. So that's the reason why I set up this spreadsheet in kind of a weird way. Alright, so let's get back to the question. So the question we're going to do is question 80, which says that you need to set the initial number infectious to 5 and the values of K1, K2, T12 and sigma 12 to the values from questions 12.76b. So if you look at the spreadsheet, what that means is that you need to enter 5 in this cell, and in the cells for K1 and the other parameters, you need to copy the values from over here. So I'll just show you how to do one. So if you do Control C and then Control V, you can paste it into there. And I've already done that for all of these parameters. So the values up here match. You'll notice these guys match each other, except for Q, which of course is different because we have a different N naught. Anyway, so this is the initial fit that they ask you to set up. And then it says use solver to find the best fit values of K1, K2, T12 and sigma 12 simultaneously. If I click on this guy, I can do that by clicking on data, and then I would need to run solver, and I'm going to enter these things all again. So click on Q, and then for the values you need to click on K1 and then hold down Control, not Shift, and hit K2, T12 and sigma 12, and then hit solve. And down here you can see there's the trial solution, and it's counting up. It's doing we're getting up to about 23 it got up to. So let's do that one more time and do solve, and it does, how many is it doing? Oh, 10, 11. Did 11 more, and we'll do it one more time. Sometimes you need to do it 3 times. Okay, and now we've got our message that all constraints and optimality conditions are satisfied, which is the message I usually look for. So if I click OK, then let's have a look at our graph. So we have our Ki of t, which is on the secondary axis over here, because that's where the label for it is. You can see that it stays a fairly constant for the first 5 to 10 days, and then it transitions down and kind of finishes transitioning around, between day 40 and day 50, which goes with the value of the this guy, the standard deviation of the transition distribution, and so it's 12.5. So 2 times the standard deviation would be 25, right? So if the mean is around 25 and the 2 standard deviations is 25, it means that 95% of the change happens at around just before day 50. Which I think it's maybe a little long, but I think it kind of makes sense. I'm not going to quibble with that. Also here we've got our distribution P of t. So here's P of t for this. It actually now starts down a little nearly at 0 and comes up and has a peak during the time of transition, right? Remember we looked at it before. The exponential growth kind of goes here, and then it transitions during this period. So that's the fact that that peak is kind of in the right place makes sense. That's the thing for question 80A. So the way that the spreadsheet, this table works, is you highlight those values, then hit Control C, and you can copy all 7 values all at once down here, and remember to paste as values. Alright, and then just double check that it actually did paste it the way you wanted. We skipped over question 79, and we're going to skip over the rest of question 80. Question 81 goes back to something that we've already modeled in one way, and now we're going to do it a second way, which is what would happen if social distancing had happened 7 days earlier. Well, in this model that we've now developed, that's pretty easy to investigate, because all we need to do is go back, and here's our transition time, and if we make that a formula, we can go equals the value that we found and then just subtract 7 days. And when I hit enter, the orange line will change and show how the infection rate per day would have changed if social distancing had happened just 7 days earlier and all the other model parameters stay the same. And as you can see, the change is pretty dramatic. If you hit Control Z, it'll go back to the original value, and then Control Y will bring you back again. So you can switch between them and see that. And if you want to calculate a number, which is what the question asks, you'll need to do some calculations calculating the area between the data in this part of the graph. Okay, so we're now finally in a position to answer the question originally posed for the video, which is estimating how many lives were lost because people didn't wear masks and practice social distancing in America. And the comparison, sort of the control group that I want to use for this comparison, is a little surprising because it's actually the folks in New York City. And the reason I picked them is that they were the epicenter of the COVID-19 outbreak, initial COVID-19 outbreak in America. And, you know, they were in trouble, and they actually locked down and did social distancing and wore masks quite rigorously for a while. And this is what their curve looks like. And so the next question is actually asking you to find the value of Ki for their period of social distancing. And it's fairly straightforward. That's question 82. And I'm not going to go through that because I think it's very similar to what we've done before in these videos. Question 83 is actually finally answering the question, and we're going to use the value, we're going to do part B because it matches what we've been talking about. We're going to use the Ki, which is actually K2, right? Change K2 to this value, which is the value for New York City. When I bring up the spreadsheet, you'll see here's the value of K2, and if I just change that number to the value from New York City, 0.07838 per day, what you want to look for is how the orange curve changes when we change the infection rate during the period of social distancing to what New York was able to achieve. And so here you see the curve goes down quite dramatically. And so again, I can use Control Z to go back, and let's get out of there. Control Z to go back and Control Y to go forward again. And so you can see the difference is really those two curves. And so again, the number of infections that were prevented is given by this area between the orange curve and the blue dots, or the orange curve and the previous orange curve. So in the question, I ask you to do some quantitative comparisons, maybe using the spreadsheet from Chapter 2. And then I have a couple of questions which I thought is kind of interesting just to see them. So this is the graph, the comparison with both of them on it. And this is the area showing the number of folks who could have been saved from infection by following New York's lead. And you'll notice that the New York curve has this fairly characteristic exponential decay, but on a linear scale it has a straight line, just like the USA data. And the reason that it appears linear is because exponential decays look linear if they're on a semi-log graph. So that's an important point to note. The section concludes with a research question and asks you to look at the data from New York, and it's actually pretty surprising, some of the things that you can discover. You have to remember though that the data came from the time when the outbreak was going pretty much out of control, and so the poor old medical folks really were having a hard time. So section 12.7 is going to be the last section, and we'll talk about what's happening now in the summer with the summer surge, and I like to talk about it in terms of the butterfly and the dragon. So getting back to PowerPoint, I'd just like to remind you about what we discovered about the number of lives that could have been saved, and it's really quite surprisingly large. And then just to remind you about where to find the materials that we've been talking about. They're at circle4.com. Don't forget to look at the top of the page for the links to the free chapters.